What's trig a study of? Angles and right triangles. I'm going to give you some identities that allow you to work with more sophisticated situations and allow us to find exact values of trig functions that are not on the unit circle, and also kind of broaden our world of the types of trig proofs that we're going to be able to deal with. This is a shortened period, so we are not going to be able to do all of our examples today, but today we're going to be analyzing, we're going to be evaluating and giving exact form answers to basically expressions that we would not otherwise be able to. We're going to be working with angles that are not the same, not the original 16 angles around the unit circle. We will be, but they will not be like in the question themselves. So example number 1 is going to be that we have the sine of 5 pi over 12. Well, we made the unit circle using 60, 30, and 45 degree, 45, 45 triangles from geometry. So the very first angle on the unit circle is what? Pi over 6. And then we go pi over 4 and pi over 3, and then we're off to the races as we count around the unit circle. We don't have any angle measures, any radian measures that have a a denominator of 12, right? We don't have any pi over 12s. But pi over 12 and pi over 6, there is a relationship there. And it's basically pi over 12 is half the measure of pi over 6. So there's potential for us to be able to evaluate this trig expression without using a calculator and giving our answers in exact format. We're not learning double angle identities today. There is an alternative way of evaluating this particular problem, but we are in 5.4 going to be learning how to work with a sum and difference of identities. So we're going to have a trig expression, or trig function, excuse me, and we're not going to have one angle inside the trig function. We're going to have the sum or difference of 2. So though I'm emphasizing the use of radian measures because that's all we do in calculus. Calculus is worked in radians when you're doing trigonometry. I don't really like finding sum and difference of angles, though, in terms of radians. I mean, you can, but then you have the whole issue with finding common denominators, and it adds a little bit of extra complexity over the problems that maybe necessarily we don't need to or want to work with or deal with. So before we start this problem, I see this angle is not in the unit circle. The directions will be evaluate and give an answer in exact format. So I know it's something I have to be able to work with or use the unit circle with. So I'm going to change this 5 pi over 12 into degrees by multiplying a geometric equivalent to 1. I'm going to multiply this by a 1/2 rotation measured in degrees and a 1/2 rotation measured in radians, or in other words, we're just multiplying by 180 over pi. So this is going to give us, of course, the pi's are going to cancel out. And when you're simplifying fractions, you should always, try to simplify. So you should be trying to divide before you multiply. So I'm not going to do 5 times 180. We're going to be trying to reduce, we want to reduce the 180 over 12. 15. Okay. So if you did not know that 180 divided by 12 is 15, you may go, well, I see a factor of 6, and do 180 divided by 6, which is 30, and 12 divided by 6, which is 2, and then realize, oh, through that reduction, where we're canceling out the common factor of 6, we have another couple of common factors that are divisible by 2, and have the answer that this gave us, which is this is 5 times 15, which is 75. So we need to analyze the sine of 75 degrees using the unit circle and giving our answer in exact format. Well, 75 degrees is not on the unit circle. But I do know a couple of angles on the unit circle that, what? Add or subtract to 75 degrees. What two angles on the unit circle in degrees either add or subtract to 75 degrees?
45 and 30.
There you go. So we're going to be analyzing the sine of 45 degrees plus 30 degrees. Okay, so we have a trig function with a sum of two angle measures. And let's say that one of these angle measures is alpha and another one is beta. There are proofs in the book that will show you, there'll be a number of right triangles involved, angles in standard position, and it's an interesting proof. It's founded in Pythagorean theorem, but I'm just going to give you these identities without proof. Phrase that. The sine of two angles added together, the sine of alpha plus beta, is going to be the sine of the first angle, the sine of alpha, times the cosine of the second angle, so sine alpha cosine beta. The sum identity for sine will have a plus sign here, and that sign stays as we go to the right-hand side of this identity. So again, the sine of alpha plus beta is the sine of alpha cosine beta plus I haven't said this for a minute, so I'm going to just make sure I write this correctly, times the cosine of alpha sine of beta. I will often say first angle, second angle. So the sine of alpha plus beta is the sine of the first times the cosine of the second plus the cosine of the first sine of the second. For some reason, that verbiage just sticks with me a little bit better than saying alpha and beta. I don't know why, but it does. Now, if you happen, I'm going to color code this, right? I want to give you, this is really two different identities. If it's the sine of alpha minus beta, so it's in pink, not blue, the sine of alpha minus beta is going to be the sine of alpha times cosine beta and then minus cosine alpha sine beta. If you're working with cosine, the cosine of alpha plus beta is cosine of the first, or cosine of alpha, cosine of the second, or cosine beta. Now, there's a little bit of a difference here, and I don't know why I'm drooping down as I write. If you have two angles that are being added together inside your cosine function, the right-hand side of this identity is going to be subtraction. So cosine alpha, cosine beta, and then because this is a sum of two angles, it's going to be minus sine alpha sine beta. If inside your cosine function you do not have a sum of two angles, but a difference of two angles, then on the right-hand side of this identity, you will not have two terms being subtracted, but two terms being added. So the sine, the plus or minus, the sum or difference that you have inside the sine function stays consistent on the right-hand side of the identity. The sum or difference that you have inside of a cosine function, those signs change for the right-hand side of the identity. Be sure you pay attention to that. It's going to take some time to work on memorizing these identities. Now, if you know the sine of alpha plus beta is the sine of alpha cosine beta plus cosine alpha sine beta, and then also know the cosine of alpha plus beta is equal to the cosine alpha cosine beta minus sine of alpha times sine of beta, then it doesn't take a tremendous amount of effort to derive the tangent of alpha plus beta. The tangent of alpha plus beta, I'm going to erase it though in a second, is quickly derived by doing the sine of alpha plus beta over the cosine of alpha plus beta. So what's going to happen is, in the numerator, we're going to have two terms that are being added, because when you have a sine of two angles added, you have an identity which has an addition sign. When you have the cosine in the denominator of two angles being added together, well, there's a sign change in that sum identity, so our denominator is going to have two terms which are subtracted. I'll derive this in another class because of our limited time, but that little recognition of the plus minus pattern yields this. the tangent of alpha plus beta is the tangent of alpha plus the tangent of beta over 1 minus the tangent of alpha, tangent of beta. And you're going to need to have a very strong grasp. You already should. We've done a few unit circle quizzes. We're going to have one very, very soon. Not within the next 20 minutes, but next week. You really need to know your unit circle. Going back to the little problem that spawned this conversation, we want to evaluate the sign of 5 pi over 12 and give our answer in exact format. No decimals out of a calculator. You won't even be able to use a calculator. The sine of 5 pi over 12, the radian measures here in sum of difference angles is a little bit, I don't like the complexity that adds, so we're converting that into degrees. We're seeing 75 is 45 plus 30. If you come up with two angles that subtract to 75, won't make any difference. You'll get the same answer. And we have the sine of two angles added. So that is going to be equal to the sine of the first, cosine of the second, plus cosine of the first, sine of the second. So if I just say first and second, I don't have to say the numbers. You know, I don't have to say, you know, I'm not changing it from 45 to 30 to sometimes 60 and negative, I don't know, whatever, 120 degrees or something. Well, you wouldn't want to do that. But at any rate, if you just say first and second all the time, maybe the memory of that identity will get ingrained into your brain and you won't have to think about it too hard instead of saying the numbers. Now it just becomes a unit circle problem. What is the sine of 45 degrees on the unit circle? Square root of 2. Ooh, that was very quick. Square root of 2 over 2. What's the cosine of 30 degrees? Square root of 3 over 2. That was a little bit slower. That's not good. Plus, what's the cosine of 45 degrees? Square root of 2 over 2. What is the sine of 30 degrees? 1/2. And our final answer in simplified form is the sine of 5 pi over 12, which is equivalent to the sine of 75 degrees, is square root of 2 times square root of 3 is square root of 6. The square root of 2 times 1 is the square root of 2. We have an addition sign in the middle. And of course, these two fractions both have a denominator of 4. So we have a common denominator, and we have our answer. So we're just applying these identities right now with our knowledge of the unit circle. We've only got 16 angles around the unit circle that we can use to create other angles. So it's not our answers. When you're doing your homework, you're going to have a lot of variations of what kind of looks like very similar or even the same answer. But there are some small changes, maybe a minus instead of a plus, or maybe the square root of 2 is first instead of the square root of 6. But you have a lot of exact form answers that all look kind of similar. But that's only, it's because the whole unit circle is made off of just two right triangles from geometry, 60, 30, and 45, 45. We got the cosine of 5 pi over 12 times the cosine of pi over 12. Plus the sine of 5 pi over 12 times the cosine of pi over 12. When you're given these two these three identities, or maybe you count it as 6, ooh, whoopsie. What's the tangent of alpha minus beta? Tangent of alpha minus tangent of beta all over, instead of 1 minus, it'll be 1 plus tangent alpha tangent beta. When you're given a problem and you recognize that the angles given are not on the unit circle, you can pretty much rest assured that you're given one side of a sum or difference identity and you want to go to the other side. We're going to see the same thing when we do double angle identities. Evaluate this expression, give me an answer in exact form. That means you're going to have to be using the unit circle. These angles are not on the unit circle. So, man, I wouldn't be given this if it didn't work out. I wouldn't be given this if it wasn't some kind of identity that we're going to have to memorize. Cosine of an angle times a cosine of another angle is then added to the sine of that same original first angle times the sine of pi over 12. What pattern does this look like now that I've written it correctly? Cosine of a first times the cosine of a second plus the sine of the first, sine of the second. Well, there's a plus sign here, so minus. So this is going to be equal to the cosine of 5 pi over 12. That's plus. This is the right-hand side of your sum and difference identity for cosine. There's a sign change, like you said, minus pi over 12. That is cosine of 4 pi over 12, which of course reduces to be pi over 3. And what's a cosine of pi over 3? 1/2. Nice. Work that out just real quick for a second. Tangent of 70 plus tangent of 50 degrees over 1 minus tangent of 70 degrees, tangent of 50 degrees. We have the tangent of 70 degrees plus tangent of 50 over 1 minus tangent of 70 degrees, tangent of 50 degrees. Wow, this looks a lot like our sum identity. The numerator is a plus, and with the numerator having an addition of 2 trig functions in it, 2 tangent functions in it, we are looking at that sum identity for tangents. So this will become the tangent of 70 degrees plus 50 degrees, which is the tangent of 120 degrees. And what's that answer? Do you know what the answer is, or do you want to help me get it?
I didn't figure that part out yet.
Well, let's go to it. At 120 degrees, what is on the unit circle? What's the x and y coordinate?
The x coordinate is negative 1/2, I think. And the y coordinate is positive square root of 3 over 2.
Awesome. And tangent is what? Tangent of theta is y over x. So our y coordinate on that point on the terminal side of the on the unit circle is square root of not 4, the square root of 3 over 2. There's your y divided by your x, negative 1/2. What's that come out to?
Negative square root of 3.
Negative square root of 3. If you need it, we're going to be, instead of dividing by negative 1/2, we're going to be multiplying by negative 2 over 1. The common factors of 2 cancel out, and we get negative square root of 3. Okay, so for our next example, we're going to be taking a look at, for the sine given, the sine of theta is 3/5, and theta is between 0 and pi over 2. And the fact that we know we're given that the tangent of beta is equal to negative 5/12, and the sine of beta is less than 0, find the sine of theta plus beta. We did not work with sum and difference identities in Chapter 4, but you have had problems in Chapter 4 that were very similar to this. You just were not given information about 2 different angles at the same time. But let's see if we can't figure this out. How do you work out the sine of theta plus beta? Sine of theta, sine of the first angle, times the cosine of beta, plus the cosine of theta times sine of beta. Wow. I hope that sounds better next week. Okay, so what is, or do we have, in the information that this equation is asking for?
The
Yeah, we know the sine of theta. The sine of theta is 3/5. So, if we know the sine of theta is 3/5, and we're blatantly told that theta is in quadrant 1, how would we be how would we figure out the cosine of theta? After you
Draw a picture.
draw a picture. Yes. Okay. So we have a picture for theta. It is in quadrant 1. We have a reference triangle. And since with trig functions you put an angle in and get the parts of the right reference triangle out, if the sine of theta is 3/5, then we know the opposite leg is 3, the hypotenuse is 5, and yes, you were absolutely correct. We're going to be doing that Pythagorean theorem on this triangle. And what is, let's say, a? Well, a squared plus 3 squared is 5 squared, and I'm trying to do some examples that I don't have to spend too much time working out the arithmetic, right? This is a 3, 4, 5 triangle. So a is going to come out to be 4. So the cosine of theta is 4/5. What other information do we have? Somebody else? Can I fill out the cosine of beta or the sine of beta?
Yes.
Not immediately, but we, of course, I mean, this is a solvable problem, so the answer of yes is correct. What are we going to do to figure out the cosine and sine of beta? Yes. So where is tangent negative? Where is tangent negative? What quadrant 2 and 4? And where is sine negative? Quadrant 3 and 4. So thank you for knowing what I was wanting you to give me as an answer. Not just the answer, but the process. So where is tangent and sine both negative? Quadrant 4. So we're drawing our picture in quadrant 4 with our angle beta rotating all the way around into quadrant 4, but we want to work with that reference triangle where it doesn't matter where this negative is. What matters is the opposite side, the opposite leg, the vertical leg is 5 and the adjacent leg is 12. It is the orientation of quadrant 4 that will tell us if it's the 5 or the 12 tell us whether it's the 5 or the 12 that's negative. Don't pay attention to where it is located in the fraction. So what is negative? The movement to the right or the movement down? Of course, it's the movement down. And really, it's the coordinate of 12, -5, and each length is positive, but, bygones. 5, 12, 13, it's a Pythagorean triple. So what is the cosine of beta? Come on. 12 over 13. What is the sine of beta? -5 over 13. So we have 36 minus 20 over 5 times 10 is 50 and 15 is 65. So our final answer is 16 over 65. All right, for our last example, we've got the sine of arc tangent of 2x plus arc cosine of x. Anderson, what do you get from an inverse trig function? An angle measure. So the arc tangent of 2x, I don't know what the angle measure is, nor are we going to find it. We may be drawing it, but arc tangent of 2x is going to give you an angle measure. What's arc cosine going to give you? Another angle measure. So to finish this problem, we need to figure out what the sine of alpha is, multiply it by the cosine of beta, and add that to the cosine of alpha times the sine of beta. How are we going to figure out the sine of alpha? How did we do all of our problems in chapter 4 first? Nearly every question was a what? You're going to draw a picture. So you have an angle in quadrant 1. What parts of the triangle do you put into tangent, arctangent? Opposite over adjacent. So the opposite leg is 2x, and the adjacent leg is 1. And a little bit of Pythagorean theorem will tell you that the hypotenuse is 4x squared plus 1. If arc cosine is going to give you a beta, and here's our drawing for beta, what parts of the triangle do you put into arc cosine? X, Y, and R kind of gets confusing because we already have x's in our problem. So, Miss, an adjacent leg over hypotenuse, and Pythagorean theorem will tell you that the other leg is 1 minus x squared. So, what is the sine of alpha? Opposite over hypotenuse. What is the cosine of beta? Well, that was given to us, wasn't it? No, well, it kind of was. What's the cosine of beta? Adjacent over hypotenuse. Let's just keep this going for a second. What's the cosine of alpha? 1 over adjacent leg over the adjacent leg over the hypotenuse. And the sine of beta? Opposite. Square root of 1 minus x squared over 1. So that should take care of every question in the homework that's not a verify this proof, which even those you should be able to do, but we'll do some proofs on Tuesday. Woo! Bam! Little rush there at the end, my apologies, but good work with everybody.